So in this video, we're going to talk about measurement and significant figures. Okay. So now, in every experimental measurement has a degree of precision, which is dependent on the measuring apparatus that is used. So like, for example, a pocket balance or electric balance that's used in the kitchen typically only goes to either, the ones place or the tenths place, like maybe a decimal place, right? While you have an expensive analytical balance that you typically find in the chemistry labs, they measure in the thousandths or the 10,000ths, so about 4 to 5 decimal places. So, for example, as I said, you may have like in a regular electric balance that you find in the kitchen, they may measure a paper clip to be like 1.1 grams, right? And if you measure that same paper clip on the analytical electric balance, it's probably going to measure 1.0957 grams. So here you can see there's a difference in precision depending on what type of apparatus that you use. Now, in this case, the analytical balance measurement gave us a lot more digits, or what we say that the digits that it's given us is significant due to the balance or due to the type of measuring apparatus that we use. So in this case, the regular pocket balance, we will say that the measurement that has given us, it has 2 significant figures, all right? While the analytical balance gave us something that has 5 significant figures, okay? And so why is this important? This is important, especially when we're measuring something and where we're either adding and subtracting or multiplying, because oftentimes when we're trying to figure out, like, for example, if we're using the paper clip and we want to figure out what's the density, right? Now you also have to measure volume, and then now when you're dividing, adding, subtracting, we have to figure out, okay, when we get the resulting data, the resulting number, how many digits is experimentally correct, all right? And so there are a couple of rules and stuff like that on determining the amount of sig figs there. But before we get to that, we want to talk about, okay, well, when we're measuring something, all right, how many digits are we supposed to record? How many digits will be deemed significant? All right. And now it really, really just kind of depends. Now, it depends on what type of device you're using. And there's really 2 different categories. Is it electronic or is it non-electronic? Now, for electronic devices, whatever digits they give you, that's pretty much how many sig figs here, right? So, like, for example, you see we're taking a mass of garlic, right? And then you see that the balance gave us that the mass of this garlic is 59 grams. How many sig figs do you have? 2. All right. Whatever the electronic device gives you, it is what it is. All right. Here's another example. Let's say you're taking the temperature of something and you're using an electronic thermometer, okay? And whatever the reading is, that's how many sig figs you have. So in this case, it's 36.5. How many sig figs are we dealing with? We have 3 sig figs, okay? And so as I said, with electronic devices, whatever the number is, it is what it is. But now, where it gets kind of tricky is if the device that we're using is not electronic. So, for example, let's just say we have this a graduated cylinder, and we're trying to measure the amount of water that we have. Okay. Now, as you could tell, this is not an electronic device. All right, it's not an electronic measuring device, and so we're going to have to kind of estimate of what's the volume that we have. So let's look at this, right? We could easily tell that we got more than 20 milliliters, right? But less than 30. All right, and then each of these calibrated marks is in, just to say each of these calibrated marks is in millimeters. So we could see that each of these calibrated marks kind of tells us, gives us an idea where we're at. So we have 1, so 21, 22, 23, 24, 25. So we have at least 25 milliliters of water, at least. Then we could see here already that we don't have 26 milliliters because that 26 millimeter calibrated mark is above the water here, right? So we know we have at least 25 milliliters. Okay, now the meniscus of the water sits around here, somewhere between the 25th and 26th. So now when you're trying to determine how many significant figures or how many digits that's to record, what you want to do is that you want to record the digits, the amount of digits that you know for sure. All right. We could easily tell that there is at least 25 milliliters. We know that for sure. There's not 26. All right. Now you're going to have to estimate one more decimal place, because what we're looking at is, okay, I could tell somewhere between 25 and 26. And so based off your observation, in my case, and to me, it looks like that I have about 25.7 milliliters of water. All right, so I'm estimating this last decimal place. All right, and you always want to do this, especially when you're using a non-electronic measuring device. Okay, so now how many sig figs I have? Well, this is the amount that I recorded. In this case, I have 3 significant figures. All right, and you'll always do this. So you always want to estimate one more decimal place, or one more basically decimal place than what the calibration is giving us. So in this case, it was calibrated to the 1's place. I'm estimating to the 10th place. If it was calibrated to the 10th place, then I'm estimating the 100th place. If the calibrated was only to the 10's place or the 100's place, then you're going to let's just say to the 100's place. Let's just keep it simple. If we're only calibrated to the 100's place, then you can only estimate to the 10's place. All right, so you always estimate that one more decimal place. Okay, now let's just say if you are now taking different types of measurements, all right, that you have found in the lab, and you have to add them or subtract them or multiply them, divide them. And oftentimes we do this a lot, especially like, for example, when we're finding density, or if we're finding speed, where there are just two different units kind of combined together to give us understanding of some type of relationship. How do we know how many significant figures the answer, the resultant is going to be, right? So in order to do that, first you need to figure out, okay, what constitutes a significant figure? Like, how do we know a number or a digit is considered to be significant? So there's a couple of rules that we have to help us determine this, all right? So like rule number 1, all non-zero digits are significant, all right? So anything between 1 to 9 is considered to be a significant figure, all right? Any number between 1 through 9. So like, for example, if we had, I'm just gonna write my examples here on this side. So if we had a number that was 123.4 grams, here in this scenario, we have 4 significant figures, okay? Because all non-zero numbers are considered to be significant, okay? Rule number 2, any zero that's at the beginning of a number, all right? So if the 0 is in the beginning, it's never considered to be significant. So it's not a significant figure. All right, so what do I mean by that? A couple examples. So like 0.0032. These zeros are not significant. So in this case, how many sig figs we have? There's these 2. All right, it's 2 sig figs. Or if we have 0.9 0.65. Well, once again, this 0 is not considered to be significant. So when we look at these digits, how many sig figures do we have? Well, we have 3 significant figures. Okay. Third case, all right. Zeros, all right, which I call they're sandwiched in. Zeros between non-zero numbers are always significant. All right. So, for example, here, if we have, here's a good 2021, right? That's the year that we're in. All right. So if you look at this zero is sandwiched in or is between non-zero numbers. So that this 0 is considered to be significant. So here we have 4 significant figures. Let's get kind of tricky. So let's say we have 0.00304. All right. Kind of pay attention to what I did here. So you see we have 4 zeros, but these zeros fall into 2 different categories here. The first set of zeros don't count because they are at the beginning. So remember, they're not significant. But this 0 here counts because it's sandwiched in between 2 non-zero numbers. All right, and so in this case, how many significant figures we have? Well, it's just 3. So we have 3 significant figures. All right, now, fourth rule, okay, to this is zeros at the end. All right, now they may be significant. It just kind of depends on the situation, right? And so it really just kind of falls down to decimal. If you see a decimal, so if the decimal is present, right, then the 0 is significant. If the decimal is absent, all right, so you don't see the decimal, then the 0 is not significant. Okay? Now we're just talking about zeros at the end of the number. So like for example, if we have 100, all right, these zeros are at the end, but you don't see a decimal. So because you do not see a decimal, the only number that's significant here is your 1. So we have 1 significant figure. Okay? But let's just say we have 100 decimal. Okay? That changes everything. All right? Because of that decimal, the zeros count. Okay? And now that we know that those zeros count, in this case, we have 3 significant figures. Okay? So that's the way that this works. So rule number 5, last but not least, but very, very important. Well, that's an ugly 5. All right, so very, very important. You have that counting objects, so measurements by counting objects or numbers due to definition, and I'm going to explain all what I mean by that. They have unlimited amount of significant figures. All right. So what do I mean by this? All right, so let's just say that you had to, for some experiment, you had to count how many dots I just drew, right? In this case, you see, oh, you counted 5 dots, right? And it's okay, how many significant figures? Because you had to count this number is considered to have unlimited amount of significant figures. All right, because it's exactly 5. Okay, unlike mass, where depending on the type of apparatus you use depends on the precision of that number, right? Are you using a scale that only goes up to the 0.1/10 place, or are you using a scale that goes all the way up to the 1,000th place? So significant figures is important for that. But if you have to count something, then that number is exact, okay? And so it has unlimited amount of significant figures, okay? Now, in terms of what I mean by a number that's based off a definition, so like an example of a definition is like conversion factors, right? And so, like, for example, we know for sure that for every 1 foot is equal to 12 inches, right? These numbers are deemed a definition because you're just converting from one thing to another. So when we're looking at 1 and 12, it has unlimited amount of significant figures. So, and which we're going to talk about a little bit later, anytime we're doing any type of conversions or mathematical equations or whatever the case is, the amount of significant figures is not going to be determined by either counting, or is not going to be determined by a definition or by a conversion factor. Okay, so there's oftentimes we have to multiply, divide, or add up, subtract our measurements to get a desired value or a desired unit, right? And so how do we determine how many significant figures are needed when we're doing these arithmetic operations, or how many decimal places are we supposed to have? So now there are two main rules. So a multiplication, division, it has its own set of rules, and addition and subtraction has its own set. So we're going to first start with the multiplying, and once again I used the wrong one, not the highlighter, but we're going to start with the multiply / division set of rules when it comes to significant figures. Okay, so now when you're multiplying, dividing, your answer cannot have more significant figure than the multiplier that has the least number of significant figures. Okay, so like for example, let's just say that you were trying to figure out density, right? We know density is grams per milliliter. All right, and so you measure the mass of a particular substance, and it turned out to be 2.2 grams. And then you measure the volume of a particular substance, and it turned out to be 10 milliliters. So the first thing that you need to do is you need to figure out how many significant figures you really have, okay? And so here, if you notice, this I have 2 sig figs, and here, all right, remember our sig figs rule, we're looking at the zero is at the very end. Does the zero count? Well, it depends. Do we have a decimal? All right, if you see, I didn't write a decimal here, so that means that 0 does not count. So in this case, we only have one significant figure. Okay, so since we're looking for density, all right, density is grams per milliliter. In this case, it's 2.2 divided by 10. All right, you put this in the calculator and you realize the calculator will tell you it's 0.22. All right, and grams per milliliter. All right, but now we have to determine, okay, how many digits do we write? All right, now as I said, when it comes to multiplying or dividing, your answer cannot be more significant or have more significant figures than the multiplier or divider, or whatever case is, that has the least number of significant figures. All right, and so in this case, we have one that was 2 sig figs. We had another one was 1 sig fig. Since the 1 sig fig is the least, our answer should only have one significant figure. All right, and so we will have to change this number is 0.2 grams per milliliter, and this would be the correct answer based off our measurements. Okay, let me show you another example. All right, I'm keeping these numbers kind of simple, but regardless of how, I guess, complicated numbers are, the concept remains the same. So let's just say that you're trying to find area, okay, of a particular table. And so you measure the table, and then you get one side is 5.0 meters, right? And you notice that the other side is 2.00 meters, okay? First, you need to determine how many significant figures you have. Well, you're looking at this, and you see, oh, I got 2 sig figs. Here, I got 3 sig figs. Remember, the zeros at the end, it all depends. I have decimal here, so the zeros count. All right, and so you put this in the calculator. All right, and the calculator, most people's calculators will just tell you 10. Right? It's just simply 10. 5 times 2. Um, Here in this case would be meters squared for the area. But we have to think about this from a scientific perspective. It's like, okay, what do we know and how many significant figures are we supposed to have in this case? All right, we have the first measurement, as I said, it has 2 sig figs. This one has 3 sig figs, so our answer should have 2 sig figs. Now, this is a really interesting situation because the answer just came out straight 10, right? And now when you're looking at this number, we have the 0 at the end. It's like, okay, we need to make that 0 significant. So how do I make this 0 significant so that way I can have 2 sig figs? Well, you just simply add a decimal point. All right, and so it'd be 10 decimal meters squared. So now here we have 2 sig fig because the multiplier that we used, the smallest number, or the smallest multiplier had 2 sig figs, okay? So our answer should have 2 sig figs as well, okay? So now, if we're adding or subtracting, okay, let's talk about those rules. So like when you're adding or subtracting, your answer cannot be more precise than the least precise number that you're either adding or subtracting. Okay, so what do I mean by that? Let's just say you're adding a couple of numbers. So we have 1.32 meters plus 0.567 meters plus 2.1 meters. Okay, so you're adding these 3 up. So like, how do you know how many decimal places or how many significant figures you're supposed to have? As I said, your answer cannot be more precise than the least precise number that you've either added or subtracted. Okay, now the best way to do this, I guess, to kind of figure this out, I'll actually line this up accordingly, and you line up the decimals. I think it's just easier that way. Okay, and then let's just do the math. So this is 7, 8, that's 8, 9. So this is 3.987 meters. Okay, now since my answer cannot be more precise than your least precise number, all right, so you have to look at these 3 numbers that you've added or subtracted, if you're subtracting, and figure out which one's the least precise. Okay, and what do I mean by that? How many decimal places does it have? So you can see that your first number has 2 decimal places. The next number has 3 decimal places. This number only goes up to the 10th. So the first one goes to the hundredths, the second one goes to the thousandths, the last one goes to the 10th. And so you see the one that goes to the 10th, the 2.1, is the least precise. It doesn't have as many decimal places, all right? So that means our answer could only go to the 10th, okay? And so what I would do is I would kind of draw a line past my least number, so that I know that anything to the left of my line is significant. Everything to the right of my line, I'm going to completely discard when I write the answer. All right, and so here to my left of my line, as I said, is significant. These are my significant figures. Anything to my right of the line, I'm going to completely discard. Okay. Now, one more thing that you have to do, you have to round, okay? And so look at the very first number to the right of your line. And so if it's greater than 5, you have to round this number, okay? So I have an 8, and so my 8's going to round up my 9. And so that means my answer will be 4.0 meters. And so this is going to be the number that I will actually write down. And so that's how you handle adding and subtracting significant figures, and that's how you figure out how many significant figures this type of operation is supposed to have.